All right, everybody, a quick video here on concavity and points of inflection. Concavity is going to describe how the shape of a graph is opening. Is the shape of the graph opening down? Does it look like a cup? For here, on this example, I have a graph, and on this left side, the graph is concave down. What that means is that the slope of the tangent line is decreasing. Let's see what that looks like here as I move the applet. As I move the tangent line from left to right, its slope is decreasing. It's getting more negative. From a steep part of the graph with a large positive tangent line slope, smaller positive, and then eventually a negative tangent line slope. If the slope of the tangent line is decreasing, that means that y double prime, or the second derivative, is less than 0. Eventually, the slope of the tangent line goes from decreasing to increasing. This is what's called a point of inflection. It's the point at which the concavity, or shape of the graph, changes from opening down to opening up. Or vice versa, it could change from opening up to opening down. At this point, the point of inflection, our second derivative is equal to 0. After the point of inflection, my function is concave up, so therefore the slope of the tangent line is increasing. I'm going from a negative slope to 0 to a positive slope. The slope of the tangent line is growing and getting bigger as I go from left to right. If the slope of the tangent line is increasing, the rate of change in the rate of change should be positive, and therefore the second derivative is equal to 0. So some re-explanation here. Concavity and points of inflection. On the left half of my graph, we are concave down, and the second derivative should be 0 whenever this happens. If the double derivative, if f double prime of x is less than 0, that implies that our function is concave down. On the right half of my graph, my function makes a cup. It's concave up. It's opening up. When this happens, the rate of change in the rate of change should be positive, and therefore the double derivative is greater than 0. My tangent line, the slope, is getting larger as I go from left to right. F double prime of x is greater than 0, concave up. Where I change concavity from concave up to concave down, or vice versa, that's called a point of inflection, and the second derivative is equal to 0. So essentially, concavity works just the same as relative extrema does for the first derivative. Double derivative negative, concave down. Double derivative positive, concave up. Double derivative 0, point of inflection. Let's look at a specific example here for our given function. We're given f of x equals 6 divided by x squared plus 3. I want to determine any concavity at f of x. Where is it concave up or concave down? Where are any points of inflection? So let's start with finding the first and second derivatives. F of x, I'm going to rewrite that as 6 times x squared plus 3 to the negative first, and then start differentiating. So f prime of x would be negative 6 times x squared plus 3 to the negative second times 2x from the chain rule. Negative 6 times 2x would be negative 12x. Divided by x squared plus 3 squared, when I move the negative exponent back down into the denominator. Negative 12x, there we go. Let's now find the second derivative. And doing so, I'll have to use the quotient rule. Negative 12x on top, x squared plus 3 squared on bottom. So low. D high, negative 1, minus high times d low. I'm differentiating the first derivative to find the second. So d low would be 2x squared plus 3 to the first times another 2x. Divided by low squared, x squared plus 3 to the fourth. All right, so here is my second derivative. Let's see what I can cancel out. On the left side of the numerator, on the right side of the numerator, and on bottom, I see a common factor of x squared plus 3. So I'm going to divide out x squared plus 3 from each. Gets rid of this, knocks this down to the third, and knocks this down to the first. So negative 12 times x squared plus 3. 2x times 2 is 4x. Times negative 12x is negative 48x squared. Because I'm subtracting that, that's now a positive 48x squared. Divided by x squared plus 3, quantity cubed. Negative 12x squared plus 48x squared would be 36x squared. Negative 12 times 3 is negative 36. Divided by x squared plus 3. Here is our final second derivative. Where this second derivative is equal to 0, I have a point of inflection. So let's set the second derivative equal to 0. That can be done by setting the top, 36x squared minus 36, equal to 0. When I add 36 and divide by 36, I get x squared equals 1. So x equals plus or minus 1. Let's make a number line to determine the sign of the second derivative for everything less than negative 1, everything between negative 1 and 1, and everything greater than 1. The sign of the second derivative will tell me if it's concave up or concave down. Remember, if the second derivative is positive, concave up. If the second derivative is negative, concave down. I change signs, I change concavity wherever the second derivative is equal to 0. And right now I know that happens at negative 1 and at positive 1. So think of a number that would be less than negative 1. Let's plug that into the second derivative. So how about we do a negative 2. 36 times negative 2 squared minus 36 divided by 0 squared plus 3, or 0 plus 3 cubed. (36 times 4 minus 36 should be positive. 0 plus 3 to the third should also be positive. And any positive divided by a positive will be positive. My function should be concave up for when x is less than negative 1. Let's now plug in a number between negative 1 and 1 to see if this interval is concave up or concave down. Let's try plugging in 0. So 36 times 0 squared minus 36 divided by 0 squared plus 3 cubed. This is 0 minus 36, so that would be a negative number. 0 plus 3 to the third is a positive number. A negative divided by a positive would make negative. Between negative 1 and 1, my function will be concave down. Let's now test a number greater than 1 to see if this interval is concave up or concave down. I'm going to go ahead and plug in 2. (36 times 4 minus 36 should be positive. 2 squared is 4 plus 3 is 7, and 7 to the third is also positive. Any positive divided by a positive is positive. What this tells me is that for when x is greater than 1, my function is concave up. Let's go ahead and write our final answer. Discuss the concavity. Where is my function concave up? Where is it concave down? Concave up from negative infinity to negative 1. And from 1 to infinity. Concave down between negative 1 and 1. I have 2 points of inflection. This is where my function will switch concavity. We'll switch how it opens. Changing from concave up to concave down at x equals negative 1, or changing from concave down to concave up at x equals positive 1. I know that this switches concavity here because these were our critical numbers of the second derivative, where the second derivative is equal to 0. Well, what's the other half of these coordinates? We need to plug negative 1 and 1 into the original equation. So let's plug in negative 1 to our original function. Negative 1 squared is 1, 1 plus 3 is 4, and 6 over 4 would be 3 halves, or 1.5. Let's plug in positive 1. 1 squared is 1, 1 plus 3 is 4, 6 over 4 is 3 halves again. So here we have all the relevant information we were able to gather about the concavity of our function. Where f of x, where 6 over x squared plus 3 is concave up, concave down, these respective intervals, and the coordinates where it switches concavity, otherwise known as the points of inflection. Here we have the shape of the graph. On Desmos on the television screen. At negative 1 and positive 1, negative 1 here and positive 1 here, this is where my function switches concavity. Everything to the left, on this side of the graph, we are concave up. Everything to the right of 1, on this right side of the graph, we are also concave up. Between negative 1 and 1, my function is just slightly concave down. At negative 1 and 1, 2 points of inflection. Thank you much for following along. Have a good day.